Imagine floating in the silent darkness of space, surrounded by billions of stars, and then suddenly, everything goes quiet. Not just silent, erased. Light itself begins to bend, time starts to slow, and the very fabric of reality seems to collapse in on itself. You're not just near something powerful, you're approaching something that should not even exist, a place where the laws of physics as we know them completely break down. This is not science fiction, this is a black hole. For decades, black holes were nothing more than terrifying equations, mathematical monsters predicted by physicists who weren't even sure they could exist in the real universe. Today, we know they are not only real, but they are everywhere. In fact, right now, at the center of our own galaxy, the Milky Way, there is a supermassive black hole quietly shaping the motion of billions of stars, including the one we orbit, our Sun. But here's the part that makes this even more unsettling. Black holes don't just sit there, they influence everything around them in ways that we are only beginning to understand. They can tear apart stars, bend time itself, and possibly even hold secrets about the origin and the ultimate fate of the universe. So what exactly is a black hole? At its simplest, a black hole forms when a massive star reaches the end of its life. For millions or even billions of years, a star exists in a delicate balance, gravity pulling inward, nuclear energy pushing outward. But when that fuel runs out, gravity wins. The star collapses under its own weight in a fraction of a second, compressing an enormous amount of mass into an unbelievably small point. This point is known as a singularity, a place where density becomes infinite, and our understanding of physics simply stops working. Surrounding this singularity is a boundary called the event horizon. This is the point of no return. Once anything crosses this invisible line, matter, energy, even light, it can never escape, not ever. That's why black holes appear completely black. They don't reflect light, they don't emit light, they consume it. But what makes black holes truly fascinating is not just their darkness, it's their ability to distort reality itself. According to Einstein's theory of relativity, massive objects warp space and time. The more massive the object, the stronger this effect becomes. And black holes, they take this to an extreme level. Near a black hole, time doesn't behave the way we experience it on Earth. If you were to somehow hover near the edge of a black hole, just outside the event horizon, you would experience time much more slowly compared to someone far away. Minutes for you could be years for someone else. This isn't a theory pulled from imagination, it's a real, measurable effect known as gravitational time dilation, and it has been confirmed through experiments, though never at the extreme scale of a black hole, yet. Now think about what that means. A black hole isn't just a cosmic vacuum cleaner, it's a natural time machine. In theory, if you could survive near one, you could witness the future of the universe unfold in what feels like a short amount of time. But survival is the problem, because black holes are not just extreme, they are violent. As you get closer, the difference in gravitational pull between your head and your feet becomes enormous. This creates a process known as spaghettification, where objects are stretched into long, thin shapes as they are pulled apart atom by atom. It's one of the most brutal phenomena in the universe, and anything that gets too close to a black hole will experience it. Yet, despite this terrifying nature, black holes are not just destroyers. In a strange and almost poetic way, they are also creators. Recent discoveries suggest that black holes may play a crucial role in the formation of galaxies. Without them, the universe might look completely different. At the center of nearly every large galaxy, scientists have found a supermassive black hole, millions or even billions of times more massive than our Sun. These giants don't just sit silently. They regulate the growth of galaxies, controlling the formation of stars by releasing enormous amounts of energy. In some cases, they shoot out powerful jets of radiation that stretch across thousands of light years, shaping the structure of the cosmos itself. And then there's something even more mysterious, something that challenges everything we thought we knew. Black holes might not be entirely black. In 1974, physicist Stephen Hawking proposed something astonishing. Black holes can emit radiation. This phenomenon, now known as Hawking radiation, suggests that black holes can slowly lose mass and eventually evaporate over incredibly long periods of time. This idea creates a paradox, one of the biggest unsolved problems in modern physics. If a black hole eventually disappears, what happens to all the information it has consumed? According to the laws of quantum mechanics, information cannot be destroyed. But if a black hole evaporates completely, where does that information go? This question has puzzled scientists for decades and has led to some of the most advanced theories in physics, including the idea that our universe might be fundamentally holographic, or that information is somehow preserved on the surface of the event horizon. But the mysteries don't stop there. Some scientists believe that black holes could be gateways, portals to other regions of space or even other universes. These hypothetical structures, known as wormholes, are solutions to Einstein's equations that connect two distant points in space-time. While there is no direct evidence that wormholes exist, the mathematics suggest they are possible. Imagine stepping into a black hole and emerging somewhere else entirely, another galaxy, another universe, or even another time. It sounds impossible, but black holes have a way of turning the impossible into something we can't easily dismiss. And yet, for all their mystery, we have only just begun to truly see them. In 2019, humanity captured the first ever image of a black hole. It wasn't a photograph in the traditional sense, but a glowing ring of light surrounding a dark shadow, the silhouette of the event horizon. It was a historic moment, confirming what had once been purely theoretical. But even that image raised more questions than answers. What exactly are we seeing at the edge of a black hole? What lies beyond it? And could there be something even more fundamental hiding at the core of these cosmic giants? Because the deeper we look into black holes, the more we realize that they are not just objects in space, they are clues. Clues about gravity, time, quantum mechanics, and possibly the true nature of reality itself. And maybe the most unsettling thought of all is this: black holes are not rare accidents in the universe, they are a natural part of it, which means the universe is not just a place of light and life, but also of darkness so absolute that it can erase everything we understand. And yet, somehow, from that darkness comes the possibility of discovery. Because if we can understand black holes, we might finally understand the universe. But to do that, we have to go deeper, much deeper. Because what we've explored so far is only the surface of the mystery. The real question is not just what black holes are, but what happens when you actually fall into one. The moment you cross the invisible boundary of a black hole, the event horizon, something extraordinary happens. Not in the way movies often show it, with dramatic flashes or explosions, but in a way that is far more unsettling. From your perspective, nothing special seems to occur at that exact point. There's no sudden jolt, no physical barrier, you simply pass through. But from the outside universe, everything about you begins to change in a way that defies intuition. To a distant observer watching you fall toward the black hole, you would appear to slow down as you approach the event horizon. Your movements would become increasingly sluggish, your signals more stretched, your image more red-shifted, fading into deeper and deeper shades of red until you eventually disappear entirely. In their eyes, you never actually cross the event horizon. You just freeze in time at the edge. This strange effect is not an illusion, it's a consequence of how gravity affects time itself. But your experience would be completely different. From your point of view, time would feel normal. Your heartbeat, your thoughts, your perception, everything would continue as usual. You would cross the event horizon without even realizing it, and that's where things begin to truly break down.
Inside the event horizon, the rules of the universe change in a fundamental way. Outside, you have choices. You can move forward, backward, left, right, but inside a black hole, all possible paths lead in one direction, toward the singularity. It's not just a place you might go, it's your inevitable future, as unavoidable as tomorrow. Think about that for a moment. In normal life, time pulls you forward, but inside a black hole, space itself pulls you inward with the same certainty. The singularity is not just ahead of you, it becomes your future. And just like you can't stop time from moving forward, you can't stop yourself from moving toward it. As you fall deeper, the gravitational forces become more extreme. For smaller black holes, this would be catastrophic almost instantly. The difference in gravity between your head and your feet would stretch you violently in a process known as spaghettification, pulling you into a thin stream of matter before you even get close to the center. But here's where it gets even more strange. If the black hole is supermassive, like the one at the center of our galaxy, the tidal forces at the event horizon might actually be relatively gentle. You could cross it without being immediately torn apart. For a brief moment, you might survive inside a black hole, fully aware that there is no escape. And what would you see? That's one of the biggest mysteries in physics. Light from the outside universe could still reach you from certain directions, but it would appear distorted, compressed into strange patterns, bending around you in ways that defy normal geometry. The entire universe might seem to wrap itself into a glowing ring behind you as you fall inward. And time itself would also behave in ways that are almost impossible to visualize. Events from the outside universe could appear to speed up dramatically. You might witness stars evolving, galaxies shifting, perhaps even the distant future of the cosmos playing out before your eyes in what feels like seconds or minutes. But eventually, all of that fades, because no matter how large the black hole is, the singularity lies ahead. And this is where our understanding reaches its limit. The singularity is often described as a point of infinite density and zero volume, a place where all the mass of the black hole is compressed into an infinitely small space. But this description is more of a placeholder than a true explanation. In reality, it represents a breakdown in our current theories. General relativity predicts it. Quantum mechanics cannot fully explain it. And so, at the singularity, our understanding of the universe simply stops. Some physicists believe that the singularity might not actually exist in the way we subword it. Instead, there could be a deeper structure hidden within, a region governed by a yet-to-be-discovered theory of quantum gravity. This is one of the biggest goals in modern physics, to unify general relativity and quantum mechanics into a single framework that can describe what truly happens inside a black hole. And this is where things take another unexpected turn. Because black holes are not isolated mysteries, they're connected to some of the most profound questions about the universe itself. Questions about the nature of space, time, and even reality.
For example, consider the idea of information.
Every object that falls into a black hole carries information about its structure, its composition, its history. But once it crosses the event horizon, that information seems to be lost forever. And yet, according to the fundamental laws of physics, information cannot simply vanish. This contradiction is known as the black hole information paradox, and it has been one of the most debated problems in theoretical physics for decades. Some scientists propose that the information is somehow encoded on the surface of the event horizon, like a kind of cosmic storage system. Others suggest that it escapes slowly through Hawking radiation, though this idea raises even more questions. One particularly fascinating proposal is the holographic principle, the idea that all the information contained within a volume of space can be described by information on its boundary. In other words, our three-dimensional universe might actually be a projection of information stored on a two-dimensional surface, and black holes provide some of the strongest clues that this might be true. If that sounds abstract, that's because it is, but it's also supported by serious mathematical work and has become a central concept in modern theoretical physics. And then there's another possibility, one that feels almost like science fiction, but is taken seriously by some researchers. What if black holes are not ends, but beginnings? What if, instead of destroying everything that falls into them, they give rise to entirely new regions of space, or even new universes? Some theories suggest that the singularity could be a kind of bridge, a transition point where matter and energy collapse in one universe and re-emerge in another. This idea is closely related to the concept of wormholes, hypothetical tunnels through space-time that could connect distant locations or entirely different universes. If such structures exist, they could redefine everything we know about reality. Travel across vast cosmic distances could become possible, the boundaries between universes could blur, and black holes, once seen as cosmic dead ends, could turn out to be gateways to something far greater. But before we get carried away, it's important to remember that these ideas are still speculative. We don't yet have direct evidence for wormholes or parallel universes. What we do have is a growing body of observations that continue to challenge our understanding. In recent years, scientists have detected gravitational waves, ripples in space-time caused by the collision of massive objects like black holes. These detections have opened a completely new way of observing the universe, allowing us to hear cosmic events that were previously invisible. Each time two black holes collide, they release an enormous amount of energy, briefly outshining entire galaxies. And as they merge, they create a new black hole, larger, more massive, and just as mysterious as before. These events are not rare. They are happening all across the universe all the time, which means black holes are not just static objects. They are dynamic, evolving, and deeply connected to the cosmic story. And yet, despite all this progress, we are still standing at the edge of the unknown, because the deeper we study black holes, the more they challenge the very foundations of physics. They force us to question what space really is, what time really is, and whether our current theories are just approximations of a deeper, more complex reality. Because if black holes have taught us anything, it's this: the universe is not obligated to make sense to us. And perhaps the most profound discoveries are waiting not in the light, but in the darkest places imaginable. But even after everything we've explored, the crushing gravity, the bending of time, the mystery of the singularity, there's an even deeper question hiding beneath all of this. A question that doesn't just challenge physics, it challenges our understanding of reality itself. What if black holes are not just objects in the universe, but the key to understanding how the universe actually works? Because when scientists study black holes, they're not just studying extreme gravity,
They're studying a place where the two most successful theories in physics collide. On one side, we have Einstein's general relativity, which describes gravity and the large-scale structure of the universe with incredible accuracy. On the other side, we have quantum mechanics, which governs the behavior of particles at the smallest scales. Both theories work perfectly in their own domains, but inside a black hole, they contradict each other. This conflict is not a small problem. It's one of the biggest unsolved puzzles in science. To truly understand black holes, we need a theory of quantum gravity, something that can unify these two frameworks into a single, consistent description of reality. And many physicists believe that black holes are the only place where we can find the answer. One of the most surprising ideas to come out of this search is that space and time might not be fundamental at all. They might be emergent, constructed from something deeper, something more basic. Just like temperature emerges from the motion of individual molecules, space-time itself might emerge from underlying quantum information. And black holes seem to support this idea in a very strange way. When scientists calculate the entropy of a black hole, a measure of its information content, they find something unexpected. The entropy is not proportional to its volume, but to its surface area. This suggests that all the information about what's inside the black hole is somehow encoded on its boundary.
This is not just a mathematical curiosity. It leads directly to the holographic principle, the idea that our entire universe might work the same way. Everything we experience in 3 dimensions could be a projection of information stored on a distant 2-dimensional surface. It sounds unbelievable, but it's one of the most serious ideas in modern theoretical physics. If this is true, then black holes are not just objects in space, they're windows into the underlying structure of reality. They suggest that the universe is not what it appears to be on the surface. And then there's another idea, one that is even more unsettling. What if the event horizon of a black hole is not smooth and empty, as general relativity predicts? What if it's actually a highly energetic boundary filled with quantum effects? This leads to the concept of the firewall hypothesis. According to this idea, instead of passing peacefully through the event horizon, anything falling into a black hole would encounter a wall of intense energy, instantly destroying it. This directly contradicts Einstein's theory, which says you shouldn't notice anything special at the horizon. So which one is correct? Right now, we don't know. This is the kind of question black holes force us to ask. They push our theories to their limits, exposing gaps in our understanding that we can no longer ignore. But perhaps the most fascinating development in recent years is how black holes are no longer just theoretical. We are now observing them in ways that were impossible just a decade ago. The Event Horizon Telescope, a global network of radio telescopes, allowed scientists to capture the first image of a black hole's shadow. That image was not just a scientific achievement, it was a confirmation that these strange objects truly exist in the way our theories predicted. And we didn't stop there. Scientists have also imaged the supermassive black hole at the center of our own galaxy, Sagittarius Asterisk. By studying the motion of stars around it, we've been able to measure its mass and understand its influence with incredible precision. At the same time, gravitational wave observatories like LIGO and Virgo have opened an entirely new window into the universe. Instead of seeing black holes, we can now detect their collisions through the ripples they create in space-time. These signals carry information about the mass, spin, and energy of the merging black holes, giving us insights that were once completely out of reach. And yet, with all this data, black holes remain deeply mysterious because every answer we find seems to lead to even bigger questions.
For example, what happens at the very end of a black hole's life? If Hawking radiation causes it to slowly evaporate, then over trillions upon trillions of years, even the largest black holes will eventually disappear. But what does that final moment look like? Does the black hole simply fade away? Or does something dramatic happen at the end?
Some theories suggest that the final stages of evaporation could release a burst of energy, a kind of cosmic explosion. Others propose that a tiny remnant might remain, containing all the information that ever fell into the black hole. But again, we don't have a definitive answer. And then there's the possibility that black holes are connected to the origin of the universe itself. Some physicists have proposed that the Big Bang could have been the result of a black hole forming in another universe. In this view, our entire universe might exist inside a black hole, part of a much larger cosmic structure. If that idea sounds extreme, consider this. The equations that describe black holes and the equations that describe the Big Bang are surprisingly similar. Both involve singularities, both involve extreme curvature of space-time, and both represent points where our current theories break down. It raises a profound possibility that black holes are not just part of the universe, but part of a larger cycle of creation and destruction. Universes giving birth to other universes through mechanisms we are only beginning to imagine. And if that's true, then the darkness of a black hole is not an end, but a beginning. But even without going that far, one thing is clear. Black holes have completely transformed our understanding of the cosmos. They have taken us from a universe that seemed predictable and orderly to one that is strange, dynamic, and filled with mysteries at every scale. They remind us that reality is not always intuitive, that the universe operates on rules that can seem impossible, even contradictory, and that our journey to understand it is far from over. Because in the end, black holes are not just about gravity or physics, they are about curiosity, about pushing beyond the limits of what we know and asking questions that don't have easy answers. What is space? What is time? What is reality made of? These are not just scientific questions, they are human questions, and black holes bring us closer to answering them than anything else we've ever discovered. So the next time you look up at the night sky, remember this. Hidden among those distant stars are objects so powerful, so mysterious, that they can bend time, erase light, and challenge the very fabric of existence. And somewhere, deep in that darkness, might lie the answers to questions we haven't even learned how to ask yet.